We can move on. So we just pointed out two problems. One of the problems was the sequence length matters, and we took care of that using attention mechanism. The other problem that we saw was this having unknown words when it comes to translation. Can we somehow get rid of those unknown words? And the idea of this paper is beautiful. This is going to find a lot of applications later on. And you can watch the video for more information and more details. But as the big picture, what are you actually doing when it comes to byte pair encoding? What is your final objective?
Reducing dimensionality.
So you want to reduce the dimensionality of your vocabulary. So you're actually correct. So you want to find a balance between the trade-off of character-based models and word-based models. And here what you're doing, if you want to tokenize your text, you can take a look at your text, cut it whenever you have space. And that's going to give you word-based tokenization. You're going to end up with a huge vocabulary, and that's going to be the actual size of your vocabulary, 1,750,000, if you keep every single word that is coming out of this process. And even then, when it comes to testing, you're going to end up with some unknowns. There's going to be some unknown words in your test data that are not part of your training data. And that's going to give you 100 million tokens. And that's the actual size of your corpus. You're counting the number of words in your corpus, all of them. And you can think of this as a measure of the sequence length or the sequence length that you're going to end up with, the total sequence length of your total corpus. And this is for German, actually. If you do character-based models, you have a few number of characters, 3,000, but then the total number of tokens, this is the sequence length in your language, is going to end up being much larger, 550 million. And the cool thing is that you're not going to end up with any unknowns, because any word in your test data, you can actually generate it using characters. Then you can take this idea to maybe not using characters, maybe using character bigrams, because you want to reduce your token size while increasing the number of types, which is your vocabulary size, or trigrams. And as soon as you try to do that, you're going to end up with unknown words. So that's not going to solve it. There is some other techniques before this, which are basically rule-based. For instance, if there is a dot at the end of your sentence, just separate the dot. Or if you're writing a word like don't, D-O-N apostrophe T, then it's better to separate them using do and N comma T rather than don't or D-O-N and then apostrophe T. Because one of them makes sense, the other one doesn't make sense. One of them makes more sense. So you can do them using rule-based, or you can do byte pair encoding, which is the method that you have here. You can end up with 0 unknown words if you do it using only a single language. And if you do byte pair encoding on the joint corpus of German and English, then you might end up with some unknowns in the end. But that's not too bad. But for a single language, you are not going to end up with any unknowns. Your token length is reasonable. It's actually equivalent a little bit slightly more than if you do nothing, just cut your text. It's slightly bigger, and then your vocabulary size is manageable. It's not in the order of 120,000 or 1,001,000. So these are manageable vocabulary sizes. That's the big picture. Qualitatively speaking, if you see a new word, these are the situations that could happen. For instance, this is the source translation. This is what it's going to be in German. So sometimes German words are actually sentences of their own. And then if you use wdict, or if you use byte pair encoding with 60K being your vocabulary size, or 90K being this other guy, then you're going to be able to actually break that German word into its components. If this is a new word, you just need to concatenate these subwords together. And that's why you don't end up with any unknowns. But how does it work in practice? You start with a dictionary, which is a pre-tokenization process. You're still cutting across your spaces. create a histogram of those vocabularies. For instance, low is going to happen 5 times. Lower is going to happen 2 times. Newest is going to happen 6 times in your corpus. Widest is going to happen 3 times. Then you're going to start with a bunch of characters that you can extract from your corpus, which could be L, O, W, and then the end of the word. Or you can equivalently have a beginning of the word. It's equivalent. And then you can just count the number of times that the pair LO is showing up in your corpus. The pair OW shows up. And then you're going to merge the ones that show up the most. For instance, ES is showing up the most, so you're just going to merge them. And then you keep repeating this process over and over again until you end up with subwords. This is the exact algorithm that you're going to run. Just copy and paste that in your Python environment and run it on perhaps this vocabulary. And then you can actually see that this happens automatically. And these merging processes, you're just going to remember, because later on, when you have a new word, you're just going to copy this process over a new word or over your new corpus. For instance, lowest, if you follow the same pattern, is going to give you low and est, and therefore you can just merge them later on. So this is beautiful. Any questions about byte pair encoding? And here byte refers to characters. Okay, was everything clear? Okay, cool. You're going to see different versions of this byte pair encoding. This was the first paper that introduced these types of ideas for language. The idea is beautiful. You can see the power. And people later on in language modeling, we are going to use that a lot. But there are some extensions to this, and we are going to cover most of them. One of the extensions that we are going to use in GPT type of models is we are going to use byte level byte pair encoding. It means that now you're reinterpreting what you're interpreting as bytes. Your bytes, if they are Unicode characters, that's going to give you byte level byte pair encoding. Here, your bytes are the actual bytes or characters that you extract from a given corpus. So byte level byte pair encoding, because Unicode characters are more universal, it's actually going to end up being very useful when it comes to GPT architecture. You're going to hear another version of this, which is word piece. Word piece is what BERT uses, BERT language modeling. It's very similar to byte pair encoding, but then the merging process is different, is based on another objective. And what is that objective? Let's say you want to merge 2 words, in this case, E and S. You go in your corpus and count the number of times that the pair ES shows up in your corpus. And then you're going to divide that by the number of times that E shows up individually. And then you're going to count that. Then you're going to also divide by the count of the number of times that S shows up individually. And then you want to maximize that objective. So you can say, if this is bigger than a threshold, I'm just going to merge. So the merging strategy is different. Here it's just based on pure counts. So does that make sense? I just went over 3 other versions of it: byte level, byte pair encoding, and word piece. Then we are going to cover later on 2 other papers. One of them is going to be based on a unigram language model. We are going to cover that. And then there is going to be an algorithm that is called sentence piece. And that's the one that people use these days. That's the most modern way of tokenizing a text. And we're going to cover that as well. But for the time being, byte pair encoding, byte level byte pair encoding, and word piece are very similar. Word piece has a different objective compared to byte pair encoding when it comes to merging characters. And byte level byte pair encoding is gonna interpret something else as bytes, the Unicode characters. So was everything clear? Okay, cool. So this is just for you if you hear these words, because when later on we are gonna work with different language models, GPT, BERT, T5, all of those language models. Each one is going to use a different tokenization process, and your results are going to end up being different if you use one tokenization for another algorithm. So you need to be consistent with whatever that you're using.